speaker is Paul Krauze from Universidade Federal de Santa Catarina, who will speak on the influence sampling of unstable flow events.
Thank you. Thank you, Elena. Thank you, Milton, for inviting. It's a real pleasure being here. This talk is of a rather a different nature in that we consider the models are in error. They may be, some terms may be in error. Parameters are uncertain. So we have to talk about uncertainties in this context. We are going to provide a prediction scheme for unstable flows in this context. My collaborator is Professor Diaz from the University of São Paulo, Department of Atmospheric Sciences. Let's have a look at this picture. This was in 2012. There was this dark squall line ranging from north to south in the coast, Brazilian coast, and I saw this squall line coming from the sea towards the continent. I said, okay, let's see what the prediction says. I had ahead of me a class. I said, okay, I'll bring this to my ODE students and we'll discuss this. Those are three sample profiles. Actually, there are two gray lines here at the bottom of the evolution of precipitation at Florianopolis at the onset of a cyclonic event in that year. And you see that the profiles diverge considerably. Those profiles were provided by different models. The cyan line is an American model. The gray lines are, one is a Brazilian model, the other one is an American model. This, at first sight, seems to be a failure, but in fact it's not a failure. These are just sample profiles. In the meteorological context, these are just sample profiles. And this is just part of the job. The second part of the job is once you have the sample, you have to process this information and try to do your best to provide a forecast, the best forecast you can provide. So what meteorologists traditionally do, they gather together once a week and analyze those pictures and emit some bulletins. This is because still today the best measure of error is your eye. It's much better than using any other norm, any other metric in the space, L1, L2, you may try, but it's much easier to look at things and say, oh, this is not going to happen. Here, those structures shouldn't appear, and this is the way you go. But as mathematicians, of course, we are trying to change things and give a measure such that we can decide what's the best forecast in this situation. I remember what happened. I was there. Actually, it rained for 5 days. So this is time 0. It rained for 5 days, and I don't think it was so strong a rain. So neither the cyan is correct, because it's telling us that it's going to rain strongly for 2 days, and neither the gray lines are correct. But the gray lines are much better performing at the end, because it rained up to the end. So actually what we want to do is to provide weight to those predictions, and these procedures should change throughout the prediction time interval. So from here to here, we would give different waves to those lines, and then we do a new analysis here, and we change the weight, and then a new analysis here, and we change the waves, because none of them are actually correct throughout the prediction time interval. And one thing to say is that the very fact that meteorologists use very different models, one made in the United Kingdom, the other one from the US, several models in Brazil, is the way to tackle this gigantic task, which is providing weather forecasts, because there are different opinions about how you should model. And this is pressures information, because there is certainly structural instability of solutions with respect to model changes. So the way to tackle it is to model a lot and provide different models, and each model is going to provide you a sample value, a different sample value. Okay. So here's the final goal is to increase the strong predictability of unstable weather events in some user-defined metric over a compact piece of the atmosphere, say above Brazil. So generally you're interested in predicting in your country. So this is taken into account, whether you are in Brazil, whether you are in the US, the different centers will use a different metric to decide how they are going to weight the different sample profiles. And what's a strong predictability? I'll refer to this later on if I have time, but the thing is that you can think of two kinds of forecasts. You may be interested in the weather here in Rio de Janeiro tomorrow at 10 o'clock, and you're just interested in this value, the state tomorrow, and you're not worried about what happens between today and tomorrow. So your prediction may oscillate. Suppose that from today to tomorrow, this is time 0, this is tomorrow. Suppose that the weather doesn't change. Your scheme may oscillate a lot, as long as it gives you a value tomorrow, and this value has a confidence interval that encompasses truth. Truth is here, and this is the confidence interval. As long as truth lies in the confidence interval, you are okay. You're happy with your prediction, but this is what we would call a weak prediction. You're only interested in the state at some time in the future. There is another kind of situation of interest. This is the one we are more familiar. Is that you'd like really to capture the variation, the time variation, the time variability of the state from today until tomorrow. So you are worried about really describing this variability within uncertainty bounds, within the confidence interval. So there are two possibilities. We can talk about predictability in the strong sense or in the weak sense. The method, well, we consider an ODE system which stems, in the present case, since we are talking about meteorology, stems from a semi-discretization of a PDE. Okay, this is how we derive the method. We write the probability of the state vector. So x is a state vector at some fixed time. I won't carry time here. Using this decomposition, which is just the definition of conditional probability. Here, x roof and x tilde are simply a splitting of the state in two groups. Okay, and instead of sampling this expression, this exact expression, we'd like to sample this other one where we changed the value of x tilde, which would be a sample value. Tilde represents different sample values. We replace this value by a single value, which is the value C. It's going to be a control value, a good estimate of the value of x tilde based on the sampling scheme, based on the sample itself. This is what people call, pretty much what people call a Rauber equalization. And if this will be a Rauber equalization scheme if this value C were a function of X roof. If you instead of having a function of X tilde, you had a function of X roof, what we are doing here would be a Rauber equalization of the sampling scheme. And Rauber equalization is good because it tells us that the variation of any estimator of a parameter theta, which is the expectation of X roof, is greater than the variance of this estimator, which is what we are going to be calculating. So we are reducing variance of the estimator. Whatever the estimator we use, we can reduce the variance of this estimator by doing this procedure. But here we are not, we don't have a function. C is not a function of X roof, it's a function X tilde. And what makes the link with Rauber is the fact that we are going to see X tilde as determining variables. And in the context of Ladizanskaya's definition of determining variables, there will be a function between X tilde and X roof. And so conditioning on C would be the same as conditioning on a function of X roof. So, and how does the scheme for sampling, how is our proposal about sampling this expression? So we consider initially an autonomous system of ODE. So phi prime is a function of phi. And then we write the Liouville equation for its dynamics. And use the associated semigroup, ETL. We use this splitting of ETL in two terms. This is a formula that some people have been using. For example, Troyon's work on dimension reduction. Weinan A at Princeton has been using this formula. It splits the action of ETL into two terms. This is what is going to separate the actions of X hat, and X tilde in our problem. That's the bootstrap in the methodology. But so far, I have no rigorous proof of this formula for these operators. Okay. Once you consider this formula, you figure out each term of this expression. Actually, there is another step between 2 and 3. You have to still split, perform an operator splitting here inside, so you carry two integrals in the expression. And then you figure out each term of the expression you obtain. And then from it, you get a short-time discrete control formula, which is this expression. It tells us that if you want to sample phi roof starting from this value with the control value for the tilde variables, which might be a good idea because C is supposed to be a good estimate of the tilde variables. You may want to go through this expression, which keeps the values of the sample values of X tilde, and just perturbs the sample values of X roof. Then you move ahead a short distance tau, and this gives you the same sample as this expression a tau unit of time ahead. Okay, you're sampling a little bit ahead of present time. And the value, the expression for dx roof is this one. Why using this instead of this? It's because here you're starting with the values, the sample values of x tilde replaced by c, which means that you're going to damage your knowledge about your uncertainty regarding the values of x tilde. It's a precious information, the sampling of x tilde, and if you replace the sampling of x tilde by this value, you're simply losing all the information about the uncertainty on x tilde. So here, you get an advantage. You don't do that. You keep this information, and since you want to sample the head variables, the training variables, it's okay. You perturb the head with this expression, and then you get a sampling for the head variables. And the same formula applies to non-autonomous ODE systems. You just, if you have an non-autonomous ODE system, you extend it to an autonomous ODE system, and you use the previous derivation, and in the end you figure what the expression you have. You switch back your time variable into a parameter, and you figure that you have the same formulas, so it's valid for non-autonomous ODE systems. Actually, I need to extend a little bit the definition of determining values that Ladishenskaya gives, because what we want to do is to control two paths. So if you're in state space and you have two orbits, you'd like to control the trailing variable, the determining variables from, say, this orbit, with the values for the determining variables from that one, so that this orbit is drawn towards the other one. But Ladishenskaya's definition of determining variables doesn't allow us to consider this picture, because for her, two orbits with same values of determining values cannot coexist. So if you are continuously replacing the values of the determining values into this one, it makes no sense in the Ladishenskaya's context to consider two different orbits. They should be already the same. Okay, so we just need to extend a little bit this concept to consider this possibility that there is you want a fast collapsing of the two, but you need to be able to do this in a finite time. So a group of variables of an evolutive system of ODEs is fast determining of the remaining variables, which we are going to refer to as training variables, if whenever continuously controlling the group of determining variables through values taken from an orbit of the system state, the flow map of the training subsystem is locally contractive for all positive t. So this is what I think is appropriate for the kind of situation we are considering. So what's the proposed scheme? We call it influence sampling. This is a word from statistics. Influence sampling means there are influence sampling formulas which are supposed to measure how sensitive is your sampling to changes, to perturbation in the sample values. And we get a formula with the derivation of this expression stems from a formula that expresses this sensitivity to perturbation in the sample values. So, okay, let's consider now as I was already mentioning, X tilde as being fast determining variables and X roof training variables. What the scheme does is to perturb the sample values of X roof into X roof plus the X roof through this formula. In this formula, phi is the dynamics of the ODE system. And the scheme also weights the new sample states according to the magnitude of the X root of this perturbation. And this is going to be, the weights are going to be defined in according to a user-defined norm, because some people will be interested in better capturing some structures. Other people would say, no, we have to focus on vortices. And so this is part of the user to decide how the waves are going to be defined according to the magnitude of the X roof. And all that is done in order to sample P of X roof given C. Okay. The scheme has a cost which doesn't scale with dimension, not at all. The expression for the cost is this one, where m is much smaller than n, so the numerator is slightly bigger than n, so the quotient here is a little bit bigger than 1. For the example we are going to see, gamma has these values. Both are close to 1.2. So this is the increase of the cost with respect to simply integrating your system and moving forward your particles. That's what we call Monte Carlo predictions. So it increases by a small factor the Monte Carlo predictions. M is the number of perturbations you're performing along the prediction time interval, and n is the number of intervals or of time tau. Tau is very small and appears in the expression of this calculation. Okay. All right, let's go straight to the results. We are interested particularly in cyclones. In South Brazil, we are right behind the swirling region of the intertropical zone. So this is a water vapor imagery in the intertropical zone, which you see affects a lot Brazil. And in South Brazil, you are right behind the swirling area. So this is why we see a lot of cyclones, or at least squall lines coming up from the sea in my area. It's an island in South Brazil. The model we shall use is a moist convective rotating shallow water system of equations proposed by Lambert, Lapère, Zetlin in 2011. The first two equations are the shallow water equations. Here you have a new term. It stems from the third equation, which is for humidity. So humidity is just advected. And there is this source term, which is the discharge of humidity. This is the expression for P. H is a Heaviside function. So whenever Q is bigger than Qs, you have a discharge of humidity, which means rain, precipitation. And this is done at a certain rate, which is given by this parameter tau. Nothing to do with the previous tau. This is, say, tau r. Of course, in a very realistic situation, this tau depends upon the clouds and the physics of the atmosphere, so it's a function of space and time. We only consider it's an uncertain value, and I've drawn in randomly from a uniform distribution with values ranging from 1 hour to 5 hours. The other parameters beta and QS have also provided uncertainty in those values, and they are drawn from a uniform distribution in this range, and this one, a uniform distribution in this other range. Numerically, I figured that the variables u, v, and q are fast determining in a sense if defined. And actually, I've also figured that UVH are fast determining of Q. UVQ is fast determining of H, and UVH is fast determining of Q. So we had two options. We decided to treat UVQ as fast determining variables, and the trailing variable is H. This is what we want to better sample. Okay. So those are the wind currents at the initial time. The first panel is the true wind current, and the second panel is the sample average estimate of this wind kernel, this wind current at time 0. What you see is that actually they are pretty close. So we are in the context that we are assuming that the sampling is unbiased. Okay, the initial sample is unbiased. There are actually small differences, but they are not strong. A meteorologist would say that this is not realistic. Okay, but this is just to begin with. We already have a proposal for treating the case where the average, the sample average estimate at time 0 is pretty different from truth, which is the biased case. But this is still current work. Should be able to show something at the workshop in a couple of months. Those red dots here are regions where truth lies outside the confidence intervals, so a problem in the sampling. Same thing for the humidity field, so Q is the humidity field. First panel is truth. This is the sample average estimate, and you have problems in the sampling. Those are areas where truth lies outside the confidence interval. But we may say that this is pretty close to what's up there, so we are still in the unbiased sampling situation. Now, this one, I've taken the H field, the water depth. I made it very biased compared to truth. The sample average differs considerably from truth. And there's a lot of red dots, meaning that truth lies outside the confidence interval. And we want to improve that without having any data at hand. The goal is to give a better picture of this in a prediction scheme. So we are going to advance in time in a prediction setting, so without any data involved. And when we use the scheme, this is what we get. Again, truth, and down here, the prediction. After 2 hours of the model time. You see that the structures are now much better captured. This important elevation here is here. Those fronts are all here. Here we are also kind of capturing what's going on. There are still a few remaining red dots, lots of them, but much fewer than in the previous situation. And this is what I wanted to show to you with this model. I have 2 minutes. Okay, so I can mention that the bias case is going to be treated soon. And I just wanted to show you a couple of figures regarding Lorentz. This is not really Lorentz. This is Lorentz plus sine functions. I've perturbed the Lorentz equations with sine functions of t. In black, you have truth. Those are the panels for the figures for variable x1, x2, x3. And in red, we have the predictions according to the scheme we are proposing. What's interesting is the fact that you have here in the middle time interval where there's intermittency. Truth lies truth leaves the attractor, and this is a time interval of unpredictability. But what's amazing is that although you go through this interval and lose predictability, the red scheme is capable of capturing truth back again in the future with high confidence, while the other methods don't. So in the context that we are used to, and in these simulations, again, we've plugged uncertainty in all the parameters, including the Lorentz 63 parameters. So this is something that we hope for. We were very surprised about this result, and then we'd like to repeat this result with partial differential equations. Being able to have contact back again in the future time with truth, although we lost contact at some moment, instead of having this traditional picture that as time comes, as we advance in time, the only thing we can hope for is to lose predictability. But this is just a hope. We don't know whether for partial differential equations this is possible. Okay, thank you very much.